Hey everyone, and welcome! Today we're diving into the fundamentals of electricity. We're going to break down all the science into simple, clear concepts to help you really get it, and of course, absolutely ace your exams. So let's start with something you do every single day, plugging in your phone. Ever just stop and wonder what's really happening inside that charging cable? It's not magic, I promise you. It's physics. And by the end of this explainer, you're going to understand it completely. So here's our game plan. First, we're going to look at what electric current actually is, the flow. Then we'll figure out what causes that flow, the push. After that, we'll learn the secret language of circuits. And finally, we'll tie it all together with the one rule to rule them all, Ohm's law. Let's jump right in.
All right, first up on our list, electric current. Let's figure out what this flow is all about. So what in the world is electric current? Well, at its very core, it's just the flow of electric charge. And a fantastic way to picture this is to think of a river. The current in a river is just how much water is flowing past a certain spot every second. Electric current? It's the exact same idea. We're just talking about charge instead of water.
And you know, in physics, we love to measure things precisely. The formula for this is actually pretty straightforward. Current, which we use the letter I for, is simply the amount of charge, Q, that flows past a point divided by the time, T, it took. It tells us exactly how much charge is zipping through that wire every single second. And listen up, because this is super important for your exams. The unit we use to measure current is the ampere, named after the brilliant French scientist André-Marie Ampère. You'll always see it written as a capital A. You gotta remember that one.
Okay, let's actually put this to work with an example straight from your textbook. So a current of 0.5 amps flows for 10 minutes. Step 1, we write down what we know, and, super important, we convert those 10 minutes into 600 seconds. Step 2, we tweak our formula to solve for charge, Q. Step 3, we just plug in the numbers, 0.5 times 600. And finally, step 4, our final answer, 300 coulombs. See, when you break it down step by step, it's not so bad. Okay, so current is a flow. That makes sense. But what makes it flow in the first place? I mean, think about it. Water in a perfectly flat pipe isn't going anywhere on its own. Electric charges need a push. And that push, well, that's our next big idea, potential difference.
That push is what we call potential difference. And a lot of times, you'll hear it called voltage. Let's go back to our water pipe. If you have high pressure at one end and low pressure at the other, the water is going to flow, right? Well, potential difference is basically the electrical pressure that shoves those charges through the wire. It's the energy or the work done to move each little bit of charge down the line.
And you guessed it, here's the formula we use to calculate that push. Potential difference, V, is equal to the work done, W, divided by the amount of charge, Q. This basically tells us how much energy it takes to move each unit of charge.
Let's lock this in with another example. How much work does it take to move a 2 coulomb charge across a 12-volt potential difference? Well, first, let's write down what we know, then we just rearrange our formula to solve for work, or W. We multiply 12 volts by 2 coulombs, and bam, we get our answer, 24 joules. And remember, the unit for work and energy is always the joule.
So now we get the what, the current, and the why, the potential difference, the flow, and the push. Now it's time to learn how to speak the universal language of electricity. How do we actually draw these ideas out? Think of this as your personal dictionary for the language of circuits. Instead of drawing complicated pictures every time, we use these standard symbols. For instance, a single cell is just a long and a short parallel line, while a battery is a few of those strung together. The bulb is just a circle with a cross, and that zigzag line is a resistor. You're going to need to know these by heart for your exams, so take a good look. They are absolutely essential. All right, this is the big one. This brings us to the law that ties everything we've learned together. We've talked about the current, the flow, and the potential difference, the push. Now let's look at the ultimate rule that connects them.
Okay, I know, that sounds a little formal, right? But all it's really saying is that if you push harder, meaning you increase the potential difference, you get more flow, you get more current. But that last part is so important, provided its temperature remains the same. Why? Well, if a wire gets hot, its atoms start jiggling around more, making it harder for the charge to push through. So this law really only works perfectly when the temperature stays nice and steady. In the language of math, that direct relationship looks just like this. V, the potential difference, is proportional to I, the current. It's a really simple idea. You double the push, you double the flow. Now, to turn this into a perfect, usable equation, we introduce one last piece to the puzzle, a constant we call R. R stands for resistance, and it's exactly what it sounds like. It's a measure of how much something in the circuit resists or fights against the flow of current. And this gives us V equals I times R. Honestly, one of the most important, most fundamental equations in all of electricity. And that's a wrap on our core lesson. We've gone through current, potential difference, and the super important Ohm's law. With these concepts in your pocket, you now have a rock-solid foundation to go and ace those exams.
Let's do a lightning-fast recap. Current is the flow. Potential difference is the push. We use standard symbols to draw our circuits. And the golden rule that connects the push and the flow is Ohm's law, V equals IR. Got it? Good.
Now, of course, this is just the beginning. If you really want to go deeper, tackle some tougher problems, and just make sure you are 100% prepared, we here at A1 Institute have got your back with things like our comprehensive notes and personalized support. So if this explainer helped clear things up for you, if you're feeling a little more confident about electricity now, do us a huge favor and hit that like button, and make sure you subscribe to the A1 Institute channel and share this with your friends so you don't miss out on our next explainer. And if you want more info about our notes, or if you're looking for some guidance, all the contact details for A1 Institute are right down there in the description below. I'm going to leave you with one last thing to think about just to spark your curiosity. We learned the simple V equals IR. But now, think about all the different lights, gadgets, and appliances plugged in all around your house. How does that one simple law manage all of that incredible complexity? Keep thinking, keep questioning, and we'll see you in the next one.